In section 7.1, we're looking at radicals and radical functions. So to find a square root of a number a, we find a number that was squared to get a. Thus, because 5 squared is equal to 25, and negative 5 squared is also 25, both 5 and negative 5 are square roots of 25. We denote the non-negative or the principal square root with the radical sign. So the square root of 25 is equal to 5. And we denote the negative square root with the negative radical sign, or negative square root of 25 equals negative 5. An expression containing a radical sign is called a radical expression. An expression within or under a radical sign is called a radicand. So the radicand is whatever appears underneath our sign, and then the actual sign is just the radical sign. So if a is a non-negative number, then the square root of a is the principal or non-negative square root of a, and negative square root of a is just the negative square root of a. So let's go ahead and simplify and assume that all variables represent non-negative real numbers. We're looking for the square root of 36. So what we're looking for is something squared that would give me 36. And so that's going to be 6. So the square root of 36 is equal to 6, since 6 squared equals 36. What about the square root of 4 over 49? What squared gives me 4 over 49? So remember with the fractions, when we square it, we square the top and bottom. So this would be 2 over 7. 2 squared would give me 4, and 7 squared would give me the 49. What about the square root of 9x to the 12th? So what squared gives me 9x to the 12th? So 3 squared would give me the 9, and x to the 6 would give me x to the 12th. So those exponent rules that we covered at the beginning of chapter 5 are coming into play here. What about negative square root of 81? So this is going to be negative 9. We know this is a negative square root because of the negative up front, in front of the radical sign. And the square root of 81 is 9 because 9 squared gives me 81. What about the square root of negative 81? Now the negative is underneath the radical, but we said that anything under the radical had to be non-negative, so this is not a real number. So can we find a real number whose square is negative 4? No, because a squared number will always give us a positive number. Therefore, a negative number will never equal a positive number. And so the square root of a negative number is not a real number. Numbers such as 1, 4, 9, and 25 are called perfect squares, since 1 is equal to 1 squared, 4 is 2 squared, 9 is 3 squared, and 25 is 5 squared. Square roots of perfect square radicands simplify to rational numbers. What happens when we try to simplify a root such as the square root of 3? Since there is no rational number whose square is 3, the square root of 3 is not a rational number. It is called an irrational number. and we can find a decimal approximation of it. To find decimal approximations, use a calculator. For example, an approximation of the square root of 3 is about 1.732, and we use the squiggly equal sign to denote that it's an approximation. To see if the approximation is reasonable, notice that since 3 is in between the perfect squares 1 and 4, when we take the square root of all three pieces, the square root of 1 is less than the square root of 3, which is less than the square root of 4. We notice that we end up with 1 is less than the square root of 3, which is less than 2. And since we found that it's about 1.732, and that number is in between 1 and 2, our result is reasonable. So we want to use the calculator to approximate the square root of 20. We're going to round it to 3 decimal places and then check to see if our approximation is actually reasonable. So let's go ahead and find the square root of 20 first, to 3 decimal places. So this is approximately 4.472. And we want to see if that's reasonable. So let's look at 20. We want to find the perfect square that's bigger than it and less than it. So the perfect square that's bigger than 20 is going to be 25, and the perfect square that's less is going to be 16. So we're going to take the square root of all 3 pieces. So we have the square root of 16 is less than the square root of 20, which is less than the square root of 25. But we know that the square root of 16 is 4. And the square root of 25 is 5. And so our decimal approximation, 4.472, is in between 4 and 5. So this is reasonable. Finding roots can be extended to other roots such as cube roots. For example, since 2 cubed is equal to 8, we call 2 the cube root of 8. In symbols, we would write the cube root of 8 is equal to 2. So what you'll notice is that with the square roots, we didn't write the index of 2, but for anything bigger than a square root, we're going to write that little index or the number with the root. The cube root of a real number, a, is written as the cube root of a, and the cube root of a is equal to b only if b cubed is equal to a. Notice that unlike with square roots, it is possible to have a negative radicand when finding a cube root. So this means that the underneath piece of our radical symbol can be negative, unlike with square roots. And this is so because the cube of a negative number can give me a negative number. So the cube root of a negative number is just a negative number. So let's go ahead and find the cube roots. Instead of looking for a number squared that would give me the radicand, this time I'm looking for a number cubed. So just like last time, when we're dealing with fractions, we cube both the top and the bottom. So what cubed gives me 8? 2 does. And what cubed gives me 125? 5 does. So the cube root of 8 over 125 is 2/5. Since 2/5 cubed is 8 over 125. What about the cube root of negative 27x to the 15th? So what cubed gives me negative 27? Negative 3 does. And x raised to what power when I cube it would give me 15? Well, remember, power raised to a power means we multiply. So 3 times what gives me 15? That would be x to the 5th. So our answer is negative 3x to the 5th, since negative 3x to the 5th cubed would give me negative 27x to the 15th. And so just as we can raise a real number to powers other than 2 or 3, we can find roots other than square roots and cube roots. In fact, we can find the nth root of a number where n is any natural number, and in symbols the nth root of a is written as the nth root of a, where n is called the index. The index too is usually omitted for square roots, but anything bigger, then we write the index. So cube roots, fourth roots, fifth roots, so on and so forth. As a helpful hint, if the index is even, such as a square root, fourth root, sixth root, and so on, the radicand must be non-negative for the root to be a real number. So if the index is even, the radicand must be non-negative. So the fourth root of 16 is 2, but the fourth root of negative 16 is not a real number. If the index is odd, such as a cube root, a fifth root, and so on, the radicand may be any real number, whether it's positive or negative. So let's go ahead and simplify the following expressions. The fourth root of 81. So we're looking for a number that when I bring it to the fourth power, I get 81. So the answer is 3, and that's because 3 to the 4th is equal to 81. What about the 5th root of negative 243? What raised to the 5th power would give me negative 243? We know it has to be negative, and we can't have a negative number because this has an odd index of 5. And so the answer is negative 3. And that's because negative 3 to the 5th is equal to negative 243. What about the 4th root of negative 81? Now my index is even, which means I have to have a non-negative number, but negative 81 is negative. So this is not a real number. What about the cube root of 64x cubed? So what number cubed gives me 64? 4 does. And as far as x goes, that's pretty easy, because x cubed would give me x cubed. So the answer here is just 4x. Since 4x cubed will give me 64x cubed. In general, radical functions are functions of the form f of x equals the nth root of x to the n. Recall that the domain of a function in x is the set of all possible replacement values for x. This means that if n is even, the domain is the set of all non-negative integers, or x, such that x is greater than or equal to 0, or from 0 to infinity. If n is odd, the domain is the set of all real numbers, or negative infinity to infinity. So we just want to keep this in mind as we find function values. Let's go ahead and plug in some values for f of x and g of x. We have f of x is equal to the square root of x minus 4, and g of x is the cube root of x plus 2. So let's look at f of 8 first. So plugging 8 into f, we have the square root of 8 minus 4. And that's the square root of 4. But the square root of 4 is just 2. What about f of 6? Same process, but this time we're plugging in 6. That's the square root of 6 minus 4, which is just the square root of 2. And we can't break that down any further. We could just get an approximation, but we can go ahead and just leave this as the square root of 2. Now let's plug into the cube root. For g of negative 1, we have the cube root of negative 1 plus 2, which is going to give me the cube root of 1. And the cube root of 1 is just 1. And one more. We have the cube root of 1 plus 2, or we have the cube root of 3. And nothing cubed would give me 3, so we can just go ahead and leave this as the cube root of 3. We could get a decimal approximation, but it's not needed in this case. And the last thing that we want to do is actually graph the square root function and the cube root function. So with the square root, we know that the index is even, so our x values have to be greater than or equal to 0. If I plug in anything negative, we would get not a real number. So let's go ahead and pick some easy numbers to plug into our square root. I'm going to pick 0, 1, and 4, just so we can get an idea of what this is actually doing. And the reason why I picked those numbers is because they will give me some nice y values to pair with my x values, so I can plot them easily. So for x equals 0, we end up with the square root of 0, which is 0. And so that gives me the value, or the point 0, 0. For 1, we get the square root of 1, which is just 1. And so I get the point 1, 1. And for 4, we have the square root of 4, which is 2. And so this gives me the point 4, 2. So let's go ahead and plot those points. We have 0, 0, 1, 1, and then we have 4, 2. And so that's the basic idea of what a square root graph would look like. Let's go ahead and look at the cube root. Now in this case, we can plug in any value of x that we want, even if it's negative, positive, or 0. So I'm going to pick some perfect cubes just to make our lives easier to plug into our function. So I'm going to pick a negative 8, a negative 1, 0, 1, and 8. You don't have to pick these exact values. I'm just picking stuff that I know is going to simplify nicely when I plug it in. So for negative 8, we have the cube root of negative 8. Which is going to give me negative 2. And so I have the point negative 8, negative 2. For negative 1, we have the cube root of negative 1, which is negative 1. So we get the point negative 1, negative 1. For 0, we have the cube root of 0, which is just 0. And so we get the point 0, 0. For 1, we have the cube root of 1, which is just 1. And so we have the point 1, 1. And then we have the cube root of 8, which is just 2. And so we get the point 8, 2. So let's go ahead and plot these points, starting with -8, -2. Then we have -1, -1, 0, 0, 1, 1, and then 8, 2. And so that's what the basic gist of a cube root graph would look like.